Okay, I guess we will get started now. There's not as many people as when I first did it, but I guess maybe it moved to a different room. Also, if you came here expecting Nicole, sorry to disappoint. So today we're going to be talking about, I'm just going to go over some things that Tom talked about earlier in class this week. Mostly we're going to focus on linear regression, which, just a reminder, if you're performing some sort of regression, you want to predict a continuous value. And then we're going to talk about logistic regression again. And this is for classification, which is when you want to predict a discrete value. And then at the end, we're going to go over gradient descent a little bit because that is a useful way to find the parameters for logistic regression. And in general, it's a very general optimization technique. You can use it a lot, so it's a good thing to be familiar with. So just to remind you of the definition. Oh, and if at any point, if anyone has questions, raise your hand and we can talk about whatever is confusing at the moment. So for regression, you want to predict a continuous valued output for your given inputs. So you have a set of labeled training examples, which would be d-dimensional x vectors, your input, and associated with each input, you have a real valued output, y. And we want to learn this function, f, that maps x to y, so we can use that to predict future values of x that maybe we haven't seen before. Predict the label or the output y that goes with them. And in the regression setting, to do this, you assume that your output y is some deterministic function of x plus some zero mean noise. Typically you assume it's Gaussian. For the specific case of linear regression, we assume a linear relationship between inputs and outputs. That is, we have the same kind of data as the general regression setting. Again, we want to learn this function that maps our inputs to our real valued output. But now we assume that this function f is a linear function of the inputs. So you maybe have some sort of intercept w0, and then for each of the features in a particular data sample, for the jth feature of the ith sample, you have some weight associated with that, and then you sum up over all of the weights and whatever the dimension of your data is. So that's the setup we have for linear regression. To go through a simple example to make it concrete, this is a one-dimensional example. So say you collected data about people's commute times. You assume that people who live farther away from campus, it's likely to take them longer to get to campus, but there is some variation. Maybe they have a lot of hills to go up or something. But so you collected information, you polled people, and said you found out how far they live from CMU, and then the time it takes them to walk to campus. And there's a general trend, as you would kind of think. So now, with this information, you want to predict the commute time for a new person who lives 1.1 miles from campus. So that would be about right here. We don't have anyone who's really living at that point. So we can't, we don't already know the answer. We'd like to predict what it's going to be. So does anyone have any ideas about what to do? Obviously, we're going to talk about linear regression, but I didn't know if anyone had any other ideas. Yeah?
Oh, you mean other ideas, other things?
Oh, you can say linear regression. It's the obvious thing. Or,
Talk about that, yeah.
oh, okay. So, yeah. What?
Just in a line for your current data, and then you can extrapolate that to predict other distances from there.
Yeah, exactly. So that's what we're going to be talking about. Does anyone have any other ideas? Just to get you thinking about ways you can predict for new values given a set of current values. Okay, well, one thing I thought someone might say would be maybe you could just look at points nearby. So say this person lives 1.1 miles away. You see that, you take whatever distance away from that point and say, oh, It's maybe the average of these values of people who live a similar distance away. So that's one approach you could do, but that's not what we're focusing on right now. But if you were thinking about other ways, you might want to solve this problem. Yeah? Yeah, so that would be a nearest neighbors approach. Yeah. So that's another way you can do it. I mean, what you ultimately decide to do depends on the problem that you have. So maybe in this case, we thought that there is kind of a general linear relationship, but if we didn't think it was a linear relationship, then something like KNN is, it doesn't make that assumption on your data that it does follow that linear relationship. So depending on what your problem is, different things may be more or less appropriate. And you can, I mean, sometimes it's interesting just to try different approaches and see how the results differ or if they're similar. Yeah, so in this case, we're going to fit a line to the data points. We are making this assumption that they do lie on a line. So if we could find this line, we could easily make a prediction for any point, because this line kind of extends. We can just, I mean, I just fit it to the points that we have here, but you could think about it extending farther up, and like, it doesn't really make sense if someone lives at negative distance from campus. So at that point, it doesn't really work. But so if we fit this line, then we'd go and we find 1.1 miles, and it looks like this person, it would take about 23 minutes for them to walk to Samuel. So what we're interested in order to make this prediction, is finding this line from the points that we have. So we're going to formally define our input, the dependent variable, the distance from campus, which was plotted there. And then the output is the commute time. And we want to predict y for an unknown x that we haven't seen before. So again, in general, in regression, you assume that the output is some function of the input plus some zero mean noise. And for the case of one-dimensional linear regression, this line, it really only has two values that define it, the intercept, W0, and the slope, W1. And we want to learn these values, the parameters of W. And the way we do this, as you've done for several different kinds of problems in class, is to maximize the conditional likelihood of the data that you see. So remember, this is our setup. We assume it's a function. You can model it as a function. And for the case of linear regression in general, we have this linear relationship between, or we assume f is a linear function of the input with this weight vector w. And just some new notation for mathematical convenience and to kind of tighten things up as we're going through. Let's put all the elements of w, including the intercept w0, into one vector. It'll be a d plus one dimensional vector. And then we're going to make this transformation of x phi of x, where we add in this extra 1 component to the top of it. And you can see if we do that, then we can rewrite f of x, which had been w0 plus like wj times xj, as then we can move this, essentially removing this w0 into the sum, because the first component of phi is going to be this 1. So then we'll multiply 1 times w0, and that's how we get that. And then the rest of the sum is still the same. So then we can write that as w transpose times phi. And then we can learn w from the data by maximizing the conditional likelihood, which we'll write just our estimate w hat, maximize the likelihood of p of y given x. Do you all want to do this interactively, or I can just click through? Doesn't matter. No preference, okay. Okay, then I'll just click through. It'll be faster. Again, if you have any questions or anything, stop. So we assume the data are independent, so we can model this joint probability as the product of the individual probabilities. And then we can take the log, because log is an increasing function. That means, say the log of x is greater than the log of y. That means that x is greater than y. So this is equivalent. And now we're going to just frame it in terms of minimizing the negative of this function. And then to recall the PDF of a normal distribution, which we assume it follows. It's just written up here. And then also the log of that. So you can see here we're minimizing over W, which in our case comes up in f of x. And the only part of this term that depends on f of x is this bit right here, the y minus f of x squared. Because here our f of x is phi transpose x. Yeah? Oh, sorry. Oh, okay. So, all right. Technically here, you didn't need to, I mean, you could still think of it as maximizing, but I'm just drawing the comparison between minimizing the least squared error and yeah. So if you keep it as maximizing, then yeah, exactly. So it's equivalent in that case. Yeah, so that's right. So yeah, the only part of the probability that it depends on W is going to be this y minus f of x squared, because for linear regression we defined f of x to be W transpose times phi of x, which was just x with that 1 added on to it. So yeah, this is the point why I switched it to be minimization. So you can see this is equivalent to minimizing the least squares error, which is like sometimes people just introduce this as we have this error function we'd like to minimize, but now you can see why the error function, that particular error function, comes up when you're assuming a linear regression model. And if the lecture notes for class show the gradient descent derivation for this, but it's also possible to derive a closed form estimate. You can solve it exactly, but that's going to be a homework problem, so we're not going to go over it now. Yeah?
Can you go over the step between going from the maximum to the minimum?
Okay, yeah, so that's what Leah brought up. It's just like, think you have a function that maybe looks like this, and you want to find the maximum. If you negate it, you're essentially flipping it across the x-axis, so it's going to look like that. So the very same point that maximized the original function would minimize the negative of that function. Any other questions? Okie doke. For this example that's one-dimensional, this line is defined by only two values, the intercept and the slope. And so you would essentially be solving this problem, but your f of x is just going to be w0 plus w1 times x. And that was all I had planned to talk about for linear regression. So we're going to move on to logistic regression now, unless anyone wants to talk about linear regression some more. So we're moving on to logistic regression. And in contrast to, well, okay, first of all, logistic regression is used for classification, which, as a reminder, you are wanting to predict a discrete value output. So a really popular example is this particular email spam or not? So that one is a binary classification. You have two outputs, spam or not spam. And in contrast to naive Bayes, logistic regression is a discriminative approach to classification. So that means we're directly estimating this probability P of y given x. That is, we're only interested in differentiating between classes y, whereas naive Bayes was generative in that it estimated P of y, the probability of a general class label, and also the probability of x given y, the probability of your data given its label, and then use this Bayes rule to calculate P of y given x. So if you have that sort of model, it explains how the data are generated given your class label. But depending on what your problem is maybe you don't really care about how the data are generated and you just want to classify your points, and in that case maybe you just want to estimate p of y given x directly instead of going this indirect route of figuring out p of y, p of x given y, and then making the transformation with Bayes' rule to flip the conditional. So the similarity between both of these, they ultimately are interested in calculating p of y given x because that's what they use to determine the label of an unseen example. But the difference is how they get at these estimates, whether it's for a discriminative approach you directly estimate p of y given x, but for the generative one it's using other pieces to calculate that in the end. So in the setting of logistic regression, suppose you have a single input x that's d-dimensional, and just for binary classification you're going to have two options for your output. And again, we're interested in learning the function that maps our input to the output. And in particular for logistic regression, we want to learn the probability of a given label given whatever the value of the input is. And in this case, the logistic function is appropriate for making probability estimates. The output, which we want to be a probability, it's always between 0 and 1. So that's important to have in a probability. And the range, the domain of the function is all real numbers. So it can take any number and give you a probability estimate. And this is the formula for the logistic function. So because this is good for modeling probabilities, logistic regression uses this logistic function, which is why it's called logistic regression. Excuse me. So we want to predict, I guess the answer's here. But so in general, the idea is if you think it's more likely for your label to be 1 for your data, then you're going to say it's 1. And if you think it's less likely than chance to be 1, so chance being 1/2, given that we have two options. So if you think the probability is less than 1/2, then you're going to predict that it's the other label, 0. So we can look at that. You have this threshold here at 1/2. So whenever it's less, the probability that y is 1 is less than 1/2. That means the probability that 0 is 1 minus this value that's less than 1/2. So that's more than 1/2. And you're going to say that everything that lies along this part of the line is in class 0, and everything that lies on this part of the line is class 1. Another way to think about this, you can think of it in terms of the point where it's on the line, where it switches from being below 1/2 to above 1/2, right there. And then everything to the left was predicted to be 0 because it's below this red line. And everything to the right is predicted to be 1 because it's above the red line where the probability is 1/2. So at that point, it's basically chance, whether it's 0 or 1. And you can see that that happens when the input to the logistic function is 0. So because of that, logistic regression is a linear classifier. We use the logistic function to estimate the probability of y given x. And then we model the probability with the logistic function. So then the decision boundary happens when this value here is 0, because that's when you switch to being right on the 1/2. Yeah?
Can you classify into more than 2 classes?
Yeah, you can classify into more than 2 classes. In that case, you modify, Tom had a slide on this in the lecture, I think. So then you have more weights that you learn. You have to, if say you have k classes, then you have to learn the weights for k minus 1 of the classes, because the last one, it has to sum to 1, so kind of whatever you figure out before, you get that. So in that case, you define the probability in terms of what the output is, or what the output is for one of the classes, and then go through the other one. So basically, you end up with another sum in your answer, and you're predicting more weights in that case. But yeah, so that's a little more complicated, but a similar, like it's an extension to this. Yeah, so the decision boundary is that point where it was your input to the logistic function was 0, which would be this value down here. So this is a line, and the classification here depends entirely on this set of weights. So this is kind of similar to the case with linear regression, where you had, because again, it's a linear classifier, so you had this set of weights that defines all of your future predictions of your model. So we want to figure out how we can calculate these weights from the data. Before I switch to the next slide, does anyone want to say how we can do this? Or no, how we're going to formulate this problem to determine what this optimal set of weights is. We've done it for a lot of things. We just talked about it for linear regression. We're going to be maximizing something, yeah? What exactly is the term that the value that we're maximizing? You're not exactly, did you say weights? We're not really maximizing the weights, right? Because we're trying to fit the weights to model our data well for prediction.
We're maximizing the prediction of the data with the estimate as we observe it.
So you're maximizing the
Maximizing since 0.5 is like the decision boundary, so are we maximizing y equals 1 half?
So the idea is we have this, we're assuming some sort of model for our data. And given that model, it tells us something about how likely our data is to occur. And we condition on what the observed value is for our labeled examples. We're trying to see how likely it is, and we want to maximize that conditioned on the label. Okay, we're going to maximize the conditional likelihood of the data. So Tom kind of went through this in class. I don't know, do you all want to go through it step by step, or would that be, I don't know if it's, was that a thumbs up? You want to? Okay. We have 1 yes and 0 no, so yeses win. Oh, you're okay, then 2 to 0, even stronger. So the first thing, we want to maximize the probability of observing our entire data sequence. So I have a little key here of what all the notation is so you can refer to it. So when I say just x and y, I'm talking about all the samples together. Again, we assume conditional independence of our data. So the probability of the entire sequence, it's equivalent to the product of the probabilities of each individual example with its output and that example itself. So this yi is going to be just a 0 or a 1, and this xi is a d-dimensional input vector. And since our output is a 0 or a 1, we'll say it's a Bernoulli with some probability pi that the ith sample is labeled 1. So then the probability that yi is 1 given xi is going to be the probability. So okay, say that the ith sample is 1. Then the probability of it being 1 is going to be pi. And since it's 1, yi is going to be 1. So this first thing will be pi. And then if y is 1, that means 1 minus yi is 0. So this entire term here goes to 1. And so then the probability of that particular sample being class 1 is pi, which is what we were left with. And conversely, say yi is 0, then the probability that yi is 0 is going to be this 1 minus p. and then raise that to the 1 minus 0, which is 1. You get 1 minus pi, and then this term is going to be 1, so when you multiply it together, it's 1 minus pi. So that's how you get the likelihood there. And then at this step, we're taking the log again, just to make solving it easier. And because we're doing the log and we have this product, we can move it to the outside and it becomes a sum. And then using more of the products of logs, you can take, so just a reminder, when you have the log of a product, that's equivalent to the sum of the individual logs, which also means that if you have an exponent in front of something, you can bring it out as a multiplicative factor in front of that log. So that's how we move from this step to this step. And then going from here to here, if you distribute this 1 minus yi across the log of 1 minus p, you're left with the 1 times this, you get the log 1 minus p, and then you have the minus yi log of 1 minus p. And when you have two logs that you're subtracting, you can make them a quotient. And then if you substitute in our definition for p, assuming the logistic model here, that's how you get these values down here. So this is the quantity that we're trying to maximize in this case. It's the conditional likelihood of our data. So does anyone want to say anything about how we're going to maximize it? Okay, then I'll say something. So the thing about this function, it's concave, which is good news, which means there's a unique maximum. So if we do find a value that we say is the greatest, it's going to be the global maximum. And our usual approach for this, if we wanted to find it exactly, would be to differentiate this function, set the gradient to 0, and solve that for the optimal weight vector. So we're happy it's concave, but in this case, there's no closed form solution for w, because if you take the gradient, set it to 0, you can't solve for w, because you have like logs of exponents and everything. So what we're going to do is use gradient descent. So we're going to switch gears and talk about gradient descent in general a little bit right now. So gradient descent is a pretty powerful optimization method. It's, you can use it for a very broad class of functions that you want to optimize that maybe you can't solve for exactly, as long as these functions are differentiable. So if you have a differentiable function f, gradient descent would choose a starting point. Lots of time just choosing it randomly works well. And then it repeats this process until nothing changes, or it doesn't change appreciably. So if you start with x0, and then at each time step k, you're going to get a new estimate for your optimum point, which is based on starting at your previous point, and then calculating the gradient of your function f, this is why it needs to be differentiable, at the current point, and then moving some length in the direction of the gradient from your current location, and then updating that as your new location. So to sum it up, you get a new update for your optimum point that's based on the previous value, and you take a little step in the direction of the gradient evaluated at your current point. So basically you're taking little steps in the direction of the gradient, so you can imagine if your function is, a nice convex function, eventually as you're moving along the direction of the gradient, you're going to end up at the bottom, which would be the optimum. And just in general, lots of times it's talked about as gradient descent if you're minimizing a function, but if you're maximizing, then it's called gradient ascent. So that's similar to the point that was brought up earlier of like, well, it's the same idea because the point brought up earlier, if you have, like if you're trying to minimize one function, that's equivalent to maximizing the negative. So if you're minimizing, you're descending, but if you're maximizing, you're going up and ascending. Yeah?
Is there any reason to do one rather than the other, or is it just?
As far as I know, and from what I'm thinking, it would be entirely equivalent, right? Because the only thing is whether you're doing the negative or positive, so that's going to change the sign of your, yeah. So you're really not changing the problem at all. Yeah, they generally talk about gradient descent, but in this case, because in this situation, we're kind of like maximizing the log likelihood, and so people generally talk about ascent, and that unless you want to phrase it as minimizing the negative likelihood, which is, I mean, it's the same thing, but sometimes you just throw in an extra word, but sometimes you do it just to be consistent with how a lot of the optimization literature goes. But yeah, it's, as far as I know, entirely equivalent. I don't see why it wouldn't be. Yeah?
Why there's no closed form?
Why there's no closed form? Yeah, so in this case, if you went through and took the derivative, I don't have this on the slides, but I know in the lecture slides, Tom went through and derived it. But if you try to do that, it's mostly because you have this, like you have the log of this sum with an exponential, and you end up having, like, some of your w's are within logs, within sums, with another, you can't separate it out. I think it's good. It's like a transcendental equation or something like that. But yeah, so in this case, we can't find the exact solution just by differentiating and setting to 0. Like, we can do that for linear regression, and you'll do that in your next homework. But for this one, it doesn't work.
I also just calculate by using gradient descent when the gradient is close to 0.
Yeah, so there are a couple different ways people sometimes do gradient descent for when they decide to stop. So one common way is just when you're taking your steps, if all of a sudden the change in your current x from your previous one, if that doesn't change too much, then you think, oh, I'm probably near the minimum or maximum anyway. And then another one is also to look at the norm of the gradient at that point. And if that is small, then say that at that point you're kind of flat, and you're not going to be able to improve by going either direction. So that's another different stopping criterion that people sometimes use for gradient descent.
So when we said there is no closed form solution, this not means the gradient can never go to 0, exactly 0. It can be very small, but not exist.
So it can be 0, we just can't solve for the values of w that would make it 0. An example? I mean, I don't have an example now. If you wanted, I mean, we can talk about it later if you wanted to try to differentiate that and solve for w. You'll probably get frustrated, but the good news is no one's been able to solve for it, the gradient of that set to 0. So, Abu's making a weird face. Yeah?
So if we choose different kinds of starting value, we expect on the result when they converge and close to 0. So if I choose different
Okay, yeah, there are a few things that can affect the convergence of gradient descent. We'll talk about one of them related to the step size, but another thing is, like, assuming your step size is okay, if you have a convex function, that means you have only one minimum. So once you find that minimum, you know it's the only one. Whereas, say, if you had a function that was more like, I don't know if you can see that. Maybe I can move one of these up. Never mind, not that one. Oh, oops. Anyway, so if you had a function like this, and say you started at this point, and you're moving along, like as you're taking steps in the gradient, you're eventually going to get down here. And because it's convex, you know that's the only, any local minimum is a global minimum, basically. But if your function looks something more like this, if you started, or to make it more obvious, or even more serious, say your function looks like this. At this point, your global minimum is this value right here. But say you started somewhere over here, you're going eventually to end up in this kind of valley right here, and you'll see if I go this way, my function value increases. If I go this way, my function value increases. So you say that this is going to be your minimum. So like from this general neighborhood, it is the minimum, but it's not the global minimum. And because of the way gradient descent works, kind of you'll fall into this basin and you won't get yourself back out to find the global one. But assuming everything with your step size is all right, and it's convex, then kind of once you get down here, that you know there's no other place that could be a minimum for you. Yeah? Yeah, so if you were trying to maximize it, you would end up going in the other direction. Because like see here, the maximum is, for this example, the maximum is infinite. So like, that's not really a solution in that case, I guess. But if you were doing gradient ascent on this and trying to maximize it, you would move in the other direction. No, okay, so this example, it does go to infinity. But if your, like say your function were the negative of this, it would be like that. And then as you're making your steps, you go in the other direction, and then you arrive at the top in that case. No, I mean you can have functions that are always bounded. Like think about the sine wave or something like that. Am I answering your question? I'm not sure.
Yeah, I did understand.
Okay. Do you have any? Like, I mean, did I answer the question that you meant to ask, and not maybe the question that I understood? Okay. Good. Yeah. So this is an example of looking at the trajectory of gradient descent for a quadratic function. This is a two-dimensional quadratic function, and I've plotted the objective levels of it here. So we started at this point over here, and then you can see there are little dots for each step that you took, moving down toward the lowest value, and then eventually we landed there at the minimum. And so now we're going to kind of talk about how one factor of this, the step size, can affect what your final result is. If you have your step size that's too big, which is over here on the right, in all of these examples we started at the same point, and the only thing I changed was the step size. So here the step size was 0.8, which you can see here was probably too big because you kind of shoot over here, like you totally overshoot your minimum, and then you try to go in the, like correct your mistake and go back, but you keep taking too big of a step. So you just kind of bounce back and forth and you never land at the optimum value. Conversely, if you have a step size that's too small, you're not going to converge in a set number of iterations because you see it kind of, like it was going in the right direction, but all of these points were really close together and never really moved that far in any one, and I think I had it do like 2,000 iterations or something here, but it never got to the maximum, or sorry, the minimum. I was trying to minimize this. But in this case, with this particular step size, it got it in just a few steps. So there are some techniques for finding a good step size. You can change the step size adaptively at each iteration. For the next homework assignment, I think we're going to have you implement logistic regression, and you should be fine with a constant step size if you find a good one. We might recommend one for you too. I'm not sure. We haven't set the problem for certain yet. So you don't necessarily need to do something fancier, but if your result isn't converging, one useful thing to do could be to look at the values that you're saying are your optimum, kind of like plot your objective and see kind of how you're moving along as you're progressing. So to sum up, this is just a reminder of what gradient descent is. You're optimizing, it works for any, it just has to be first order differentiable. All you need is the gradient. And you refine your initial estimate of your point by moving in the direction of the gradient. And if you're, so this is for gradient descent, but gradient ascent is similar, and Tom had like those slides. He derived it, this update rule and everything in the lecture slides. So that will be helpful for you all when you're implementing logistic regression in your homework. So that's all I had prepared for this recitation. So if any of you have any questions or want to talk about anything different, we can. We have about 10 minutes left or so, 10, 13 minutes. So we can talk about anything, or you can leave. So if you have any questions, talk about them now. Yeah?
I was actually thinking of the circle as a function, and you're trying to either minimize or maximize from some point on the circle. So I'm thinking how this works, whether that's one or
Well, I guess technically a circle isn't a function, right? Because for a given output, or sorry, a given input, you have different kinds of outputs, right? Well, also in that case, you do have a given minimum and maximum of a circle, right? Like you assume, say your axis is here, this point's going to be your maximum, this point's going to be your minimum. So in that case, you could think of it almost like the idea of how gradient descent would work. Well, okay, so with gradient descent, the information you're getting from the gradient is kind of the direction that the function is changing. So if you're trying to minimize it, you know from your gradient that's going to get you going in the correct direction. And you'll end up going downward toward your minimum.
So what I actually was thinking, when I was thinking of a function like the value rho x, that it has a boundary, it does not tend towards infinity on this side. It's not like going with x squared like
Okay. Like, do you want to think about like a section of a sine wave or something like that? Because like that's bounded, and we're not going to.
yeah, let's say like a part of it.
Yeah.
So if you're like the bottom or the bigger, and you're trying to maximize it, you don't know which side to go because both have an increasing gradient, and it might be the case that the direction that in which you prefer to go to is not an
Okay. So say we have this sine wave, and where do you want to start on it? Like, what do you want your starting point to be?
Yeah, so you're starting small.
Like, you're starting right here?
And it would be the case that
Oh, okay. Okay, yeah. No, I see what you're saying now. So in this case, because you truncate it here, I mean, I guess if you're just doing gradient ascent, you. Oh yeah, that's, so you just want to think about this part? Like, oh, so from the right side part here. Oh, okay, well in this case, you would get to the edge of your domain and know that you don't have anything beyond that. Like if we're just truncating it to this part, you would get to the end of your domain and you wouldn't try to. So the gradient has to do with kind of the steepness of the function, how much it's changing at that point. So that depends, that's a property of the function. Huh?
It might be the case that it's not steep enough at that point, but the slope actually begins to increase at a much faster rate than it moves on upward. Where your local approach is not actually working, even though it's an increased slope. It points you in the direction where it's kind of a gradual slope. But the other side, even though it has a lesser slope, it begins to grow much more rapidly and you have a better maximum.
Maybe we could talk about this later because I'm not sure that we're thinking of the same type of function or understanding what, yeah, I'm not sure that I'm understanding what you're saying and I don't know if it's coming across or not. Okay, so another thing is I would want to think more about the case where you bound it at the end. Because in general, we were talking about kind of your domain is all real numbers. But if you have these endpoints, then you don't really, like your function kind of ends there, so you don't know what's happening beyond that because it's not defined in that interval. Yeah?
Very different question.
Mm-hmm.
How do we tell that the function is concave? Maybe that's like calculus is totally unrelated.
Yeah, so simple answer. I don't know it off the top of my head. I mean, you could look at the second derivative and see, and if the second derivative is negative, then it's concave at that point. But
I guess what I mean is, how do we know that it only has one global maximum? I guess that has to do with the order of the derivative. Is that right?
sorry, what?
How do we know that it only has a global maximum?
And not, okay, so that's because it's concave. Like that's basically the definition of concavity. That follows.
Because the derivative is only like because
Wait.
the derivative only has, or because the derivative only has, I'm not sure how to.
Okay, so yeah, I don't remember, I don't remember why we know that it's concave, but one way to determine if a particular thing is concave or not is to look at the second derivative. And the sign of that indicates whether it's convex or concave at that point. Yeah, but I'll look into that and tell you. Yeah, thanks. So the grades for, homework 2. So wait, that was, okay. When was homework 2 due? Okay. I think we are, I wasn't one of the graders for that assignment, so I'm not quite sure what's on the front for that. But it should be soon if it were over a week ago. But I think they'll post, make a Piazza post or something when the grades are out, but it should be soon. Okay, I guess we're finished.